Hello students, in today's lecture we will discuss about the topic quantum mechanical model of atom, which is given in unit 2 of NCERT syllabus. This is the final lecture of the unit 2, that is structure of atoms. This is a very interesting, important and a very vast topic and requires your apt attention. Please listen to the lecture very carefully and note down all the important points. I welcome you once again. Quantum mechanical model of atom. Classical mechanics, based on Newton's law of motion, successfully describes the motion of all macroscopic objects such as falling stone, orbiting planets, etc., which have essentially a particle-like behavior as shown in the previous sections. However, it fails when applied to microscopic objects like electrons, atoms, molecules, etc. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter, especially for subatomic particles, and the uncertainty principle, the branch of science that takes into account this dual behavior of matter, is called quantum mechanics. Quantum mechanics is a theoretical science that deals with study of motions of microscopic objects that have both observable wave-like and particle-like properties. The fundamental equation of quantum mechanics was developed by Schrodinger, and it won him the Nobel Prize in the year 1933. Let us quickly run through the life history of great scientist Erwin Schrodinger. Erwin Schrodinger, an Austrian physicist, received his PhD in theoretical physics from University of Vienna in 1910. In the year 1927, Schrodinger succeeded Max Planck at the University of Berlin. In the year 1933, Schrodinger left Berlin and returned to Austria in 1936. Later he moved to Dublin, Ireland, where he remained for 17 years. Schrodinger shared the Nobel Prize for Physics with P.A.M. Dirac in the year 1933. And the fundamental equation of quantum mechanics developed by Schrodinger incorporates wave-particle duality of matter as proposed by de Broglie. For a system such as an atom or a molecule whose energy does not change with time, Schrodinger equation is written as h hat psi equals E psi, where h is a mathematical operator called Hamiltonian, and psi psi is a wave equation. E is the energy. The total energy of the system takes into account the kinetic energies of all subatomic particles, electrons, nuclei, the attractive potential between electrons and nuclei, as well as repulsive potential among electrons and nuclei individually. Solution of this equation gives the values of E energy and wave equation psi. Hydrogen atom and Schrodinger equation. When Schrodinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy, that is, the possible electron levels that the electron can occupy, and the corresponding wave functions psi of the electron associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by the by a set of three quantum numbers. These quantum numbers are principal quantum number, whose symbol is letter small n, azimuthal quantum number represented by letter small l, and magnetic quantum number m subscript l, ml, arise as a natural consequence in the solution of Schrodinger equation. When an electron is in energy state, the wave function corresponding to that energy contains all information about the electron. The wave function psi is a mathematical function whose values depend on the coordinates of the electron in the atom and does not carry any physical meaning. So please remember, the wave function psi as such does not carry any physical meaning, whereas psi square has some meaning, which we will discuss later on. Such wave functions of hydrogen or hydrogen-like species with one electron are called atomic orbitals. So wave functions are orbitals, atomic orbitals, and wave functions pertaining to one electronic species are called one electron system. The probability of finding an electron at a point within an atom is proportional to mod psi square at that point. So the probability of finding an electron at a point within an atom is proportional to mod psi square. The quantum mechanical results of hydrogen atom successfully predict all aspects of hydrogen atom spectrum, including some phenomena that could not be explained by Bohr model. Application of Schrodinger equation to multi-electron atoms present a difficulty. Scientists found that predicting the applications of a hydrogen atom easier, but the application of this Schrodinger equation to multi-electron atoms was a difficulty. The Schrodinger equation cannot be solved exactly for multi-electron atom. The energies of orbital in multi-electron atoms depend on quantum numbers n and l. Important features of quantum mechanical model of atom. Quantum mechanical model of an atom is the picture of the structure of atom which emerges from the application of Schrodinger equation to atoms. The following are the important features of quantum mechanical model of atoms. Point number 1. The energy of electrons in atom is quantized. For example, when electrons are bound to the nucleus in atoms. That means the energy of electrons is quantized when the electrons are bound to the nucleus in the atom. Point number 2. The existence of quantized energy levels is a direct result of wave-like properties of the electrons and are allowed solutions of Schrodinger wave equation. Both exact position and exact velocity of an electron in an atom cannot be determined simultaneously. That is, according to Heisenberg uncertainty principle. Thus, the path of an electron in an atom can never be determined or known accurately. This sentence you please underline. An atomic orbital is the wave function psi for an electron in an atom. Please note that psi is a wave function psi is an atomic orbital. Whenever an electron is described by a wave function psi, we say that the electron occupies that orbital. Since many such wave functions are possible for an electron, there are many atomic orbitals in an atom. Thus, the one electron orbital wave functions or orbitals form the basis of electronic structure of atoms. In each orbital, the electron has a definite energy. An orbital cannot contain more than 2 electrons. This also you please note down. In a multi-electron atom, the electrons are filled in various orbitals in order of increasing energy. For each electron of a multi-electron atom, there shall therefore be an orbital wave function characteristics of the orbital it occupies. All the information about the electron in an atom is stored in its orbital wave function psi, and the quantum mechanics makes it possible to extract this information out of psi. Next point is about psi square. Psi square, which states that the probability of finding an electron at a point with an atom is proportional to the square of the orbital wave function, that is psi square at that point. Psi square is known as probability density. In the previous point we studied about psi, which was wave function, whereas psi square is a probability density and it is always positive. From the value of psi square at different points within an atom, it is possible to predict, underline, predict the region around the nucleus where electrons will most probably be found. Orbitals and quantum numbers. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and orientation. Let us get some insight into the difference between orbital, and its importance, which is stated in the inset box. An orbit as proposed by Bohr is a circular path around the nucleus in which an electron moves. A precise description of this path of electron is impossible. Please underline impossible according to the Heisenberg uncertainty principle. Bohr's orbits therefore have no real meaning and their existence can never be demonstrated experimentally. This was proved by Heisenberg. Now, after discussing about orbit, we will discuss about atomic orbital. An atomic orbital is a quantum mechanical concept and refers to one electron wave function psi. So, the concept refers to one electron wave function psi in an atom. It is characterized by the three quantum numbers which we are going to study in subsequent slides. These quantum numbers are represented by symbols n, small l, and m, l, m subscript l, and its value depends on the coordinates of the electron. Psi has by itself no physical meaning, but square of the wave function, that is psi square, which has a physical meaning. Psi square at any point in an atom gives the value of probability density at that point. Probability density psi square is the probability per unit volume, and product of psi square and a small volume called a volume element yields the probability of finding electron in that volume. The correct reason for spying small volume element is that psi square varies from one region to another space, but its value can be assumed to be constant within this small volume element. The total probability of finding electron in a given volume can then be calculated by the sum of all the products of psi square and the corresponding volume elements. It is thus possible to get the probable distribution of an electron in an orbital. So we will continue our discussions on orbitals and quantum numbers in the next point. An orbital of smaller size means there is more chance of finding electron near the nucleus. Similarly, shape and orientation mean that there is more probability of finding the electron along the certain directions than along others. Atomic orbitals are precisely distinguished by what are known as quantum numbers. Please read once again. Atomic orbitals are precisely distinguished by the quantum numbers. Each orbital is designated by three quantum numbers n, l, and m subscript l. Now we will study in detail about this quantum number. The first one is principal quantum number, represented by the symbol letter small n. Please recall the Bohr's model, which is just shown for understanding purpose, and continue with our study. Here in principal quantum number, n is a positive integer with value n is equal to 1, 2, 3, etc. etc. Please note that the range of n starts from positive integer, that is 1. It does not start with 0. Therefore, its values are positive integer 1, 2, 3, etc. N equal 1 corresponding to K shell as shown in the figure, K orbital. N is equal to 2 is L, capital L orbital. N is equal to 3 is M shell. And M is equal to 4 is an orbital, and so on. N will be still 5, 6, 7 like that. It has got different meaning. The central point in the diagram is a nucleus, and all the orbitals are increasing as shown in the figure. increasing orbital energy. The principal quantum number determines the size and to large extent the energy of the orbital. The principal quantum number is the main shell or orbit of an electron. Number of orbitals, please note underline orbitals, is equal to n square. Maximum number of electrons present in the shell is given by 2n square, where n is the principal quantum number. So electrons are 2n square, orbitals are number of orbitals are n square, number of electrons are 2n square. Size of an orbital increases with increase of principal quantum number n. So here you see the size is increasing. As we increase the number of orbital, the size also increases. Since energy is required in shifting away the negatively charged electron from positively charged nucleus, the energy of the orbital will increase with increase of n. The principal number explains the main lines of spectrum. The angular momentum can be calculated by using the equation mvr is equal to nh by 2pi. The left hand side is potential energy, mass into velocity into radius equals nh by 2pi. Now let us work out a small example. Question. What is the total number of orbitals associated with the principal quantum number n is equal to 3? Answer is, we know that the number of orbitals is given by n square. So here n is equal to 3, therefore the answer is 9. Azimuthal quantum number represented by the symbol small l. Azimuthal quantum number L is also known as orbital angular momentum or subsidiary quantum number. It defines three-dimensional shape of the orbital. For a given value of n, L can have n values. So L depends on n. L can have n values ranging from 0 to n minus 1. Please note it starts from 0. The value of L starts from 0, whereas the value of primary quantum number n starts from 1. So here L starts from 0 to n minus 1. That is, for a given value of n, the possible values of L are L is equal to 0, 1, 2, etc. up to n minus 1. This you can observe in the table shown on the screen. So the value of n starts from n and it extends. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, and on. Whereas L is equal to n minus 1, that is 1 minus 1 equal to 0. So it starts from 0 and extends up to n minus 1, that is 5 minus 1 is 4. Each shell consists of one or more subshells or sublevels. So each shell consists of one or more subshells. The subshells are designated by letters S, P, D, F. So here in the third column, S represents the subshell. P, S, P, D, F represents the subshells. The number of subshells in a principal shell is equal to the value of n. So if n is equal to 1, the 1 is the number of subshells is 1. And if n is equal to 2, the number of subshells are 2. See, this is one and this is another one, and so on. It conveys the information about the relative energies of the subshells. The azimuthal quantum number explains the fine structure of line spectrum. Orbital angular momentum of electrons can be calculated as mu L is equal to square root of L into L plus 1 into h by 2 pi. Let us take one example. Using SPDF notations, describe the orbital with the following quantum numbers. So here in this example, he has given the quantum number. A number of questions are sub questions are there. You have to find the explain the orbital. So question number A, n is equal to 2, L is equal to 1. N is equal to B is n is equal to 4, L is equal to 0. And part C is n is equal to 5, L is equal to 3. And part D is n is equal to 3, L is equal to 2. So let us give answers. So in part A, question number n is equal to 2 and L is equal to 1. So here please see the table. For n is equal to 2, L is equal to 1, it is 2p. This is the item. Next one is part B. N is equal to 4 and L is equal to 0. Orbital 4. So this is N is equal to 4 is here and L is equal to 0 here. So this answer is 4s. Next question. Part C. N is equal to 5 and L is equal to 3. So n is equal to 5 is here and L is equal to 3 is here. So it is 5f. Therefore D is n is equal to 3 and L is equal to 2. So n is equal to 3 is here, L is equal to 2. So it will be 3D. You have to remember and work out. Magnetic orbital quantum number represented by letter small m subscript L. ML gives information about the spatial orientation of the orbital with respect to the standard set of axes, coordinate axes, that is x-axis, y-axis and z-axis. For a particular value of L, the value of ML varies between minus L to plus L, including 0. A total of 2L plus 1 values are possible and these values are given by, say for example, ML is equal to minus L minus of L minus 1 comma minus of L minus 2 etc and 0, and then these are all negative numbers and right side of 0 are all positive. So 0, 1 etc. L minus 2 L minus 1, etc., etc. Say for example, if the value of L is 2, then we have values varying from minus 2 to plus 2, that is minus 2, minus 1, 0, plus 1 and plus 2. So altogether there will be 5 numbers of orbitals. This you can substitute, say for example 3, 4, etc. and you will find that the number of orbitals depend on the value of L given by the formula 2L plus 1, and its number of orbitals are 1, 3, 5, 7 and 9. It should be noted that the values of ML are derived from L and that the values of L are derived from N. This line also you underline. Each orbital in an atom therefore is defined by a set of values of N, L and ML. An orbital described by quantum numbers n is equal to 2, L is equal to 1 and ML equal to 0 is an orbital in the p subshell of the second shell. Electron spin S. The three quantum numbers labeling an atom orbital can be used equally well to define its energy, shape and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms. That is, some of the lines actually occur in doublets, each two line closely spaced, triplets, three lines closely spaced, etc. This suggests the presence of few more energy levels than predicted by three quantum number. Hence, there is fourth quantum number. In the year 1925, George Uhlenbeck and Samuel Goudsmit proposed the presence of the fourth quantum number known as the electron spin quantum number, represented by the symbol m, small m subscript s. An electron spins around its own axis much in the same way as Earth spins around its own axis while revolving around the Sun. In other words, an electron has, besides charge and mass, intrinsic spin angular quantum number. Ms indicates the direction of electron spin. It can be clockwise or anti-clockwise. The spin angular momentum of the electron, that is a vector quantity, can have two orientations relative to the chosen axis. These two orientations can take the values of plus half and minus half. These are called two spin states of electron and are normally represented by two arrows, that is arrow upward, spin up and arrow down, spin down. Two electrons that have different ms values, 1 plus 1 and minus 1, are said to have opposite spin. Please see the figure. This representation has been indicated, one for hydrogen atom, one electron spin up, and helium 2, one up and one down, spin down. An orbital cannot hold more than two electrons, and these two electrons should have opposite spins as shown in the figure. Spin angular momentum equals under root s into s plus 1 into h by 2 pi. Shapes of atomic orbitals. The orbital wave function, or psi for an electron, is an atom has no meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave function as a function of r, that is the distance from the nucleus, are different. Shape of an orbital is given by the total probability density psi square for both radial path and angular path. According to German physicist Max Born, the square of the wave function at a point gives the probability density of the electron at that point. The region where this probability density function reduces to zero is called a nodal surface or simply nodes. Please note once again, the region where the probability density function reduces to zero is called the nodal surface or simply nodes. For an atom of principal number n, radial nodes is equal to n minus L minus 1. And angular node is equal to L. Therefore, total nodes will be equal to sum of the two, that is n minus 1. Shape of the s orbital. The probability of finding an electron is equal in all directions at a distance from nucleus is same. The shape of orbital in s orbital is spherical. This is for n1s as shown in the diagram on the right hand side. That is the top figure. Shape of the p orbital. These are the three shapes of the p orbital. The probability of finding a p electron is maximum in two dumbbells. The shape of this orbital is two dumbbells type. Two dumbbells lobes. The shape is dumbbell. The p orbital possesses one nodal plane passing through the nucleus. So it will be one orbit passing through the nucleus. Shape of the d orbital. This is the d orbital shown here. Depending on the probability, d orbital have clove leaf like shape. The shape is that of clove leaf. There are 5 orbitals. So one is dxy, dxy is here, dxy is here, dyz is here, and dx square minus y square is this shape, and dz square is this is the one. Each d orbital has two nodal planes. Energies of orbitals. The energies of an electron in hydrogen atom is determined solely by the principal quantum number. Thus, the energy of the orbitals in hydrogen atom increases as follows. 1s less than 2s, that is equal to 2p less than 3s, that is equal to 3p, that is equal to 3d minus 4s equals to 4p, that is equal to 4d less than 4f, that is less than so on and so on. Let it be equation 1. Please see the figure here, 1s, 2s, 3s. The energy level which is not to scale is shown here in this pinkish color. This is for S and the P is here and D is here in the third column. The orbitals have same energy. Having the same energy are called degenerate. Same energy is degenerate. The first orbital in hydrogen atom, as said earlier, corresponding to the most stable condition and is called the ground state. This is the first orbital. Residing in this orbital is most strongly held by the nucleus. An electron in 2s, 2p or higher orbitals in hydrogen atom is excited. Here 2p, 2s, 2p, these In these orbitals, electrons in these orbitals 2s, 2p, 3s, 3p, 3d, etc. are in excited state. 1s is in the ground state. These 1s electrons are tightly bound to the nucleus. The energy of an electron in a multi-electron atom, unlike that of the hydrogen atom, depends not only on principal quantum number shell but also on azimuthal quaternion number subshell. That is, for a given principal quantum number, SPDF will have different energies. So, for a given principal number n, SPDF will have different energies. The lower value of n plus L for an orbital, the lower is its energy. So the lower value of n plus L for an orbital, lower is its energy. If the two orbitals have the same value n plus L, the orbital with the lower value of n will have the lower energy. The energies of orbitals in the same subshell decrease with increase in the atomic number ZeF. This you will study in higher classes. Filling of orbitals in an atom. The filling of electrons into the orbitals of different atoms takes place according to the Aufbau principle, which is based on Pauli's exclusion principle, the Hund's rule of maximum multiplicity, and the relative energies of the orbitals. Aufbau principle. The word Aufbau in German means building up. The building up of orbitals means filling up of orbitals with electrons. This principle states that in the ground state of atoms, the orbitals are filled in the order of their increasing energies. In other words, electrons first occupy the lowest energy level orbital available to them and enter into the higher energy orbitals only after lower energy orbitals are filled. Pauli exclusion principle. The number of electrons to be filled in various orbitals is restricted by exclusion principle given by the Austrian scientist Wolfgang Pauli. According to this principle, that is Pauli exclusion principle, no two electrons in an atom can have the same set of four quantum numbers. Pauli exclusion principle can also be stated as only two electrons may exist in the same orbital and these electrons must have opposite spin. Hund's rule of maximum multiplicity. This rule deals with the filling up of electrons into the orbitals belonging to the same subshell, that is, orbitals of equal energy called degenerate orbitals. It states, that is, the Hund's rule of maximum multiplicity states that the pairing of electrons in the orbitals belonging to same subshell, that is, the subshells may be P, D or F, does not take place until each orbital belonging to that subshell has got one electron each and it is singly occupied. So, the filling up pairing of electrons in the orbitals belonging to same subshell does not take place until each orbital belonging to that subshell has got one electron each, that is singly occupied. The diagram on the screen shows the distribution, the order of filling of orbitals. Please go through it in detail. Electronic configuration of atoms. The distribution of electrons into orbitals of an atom is called its electronic configuration. If one keeps in mind the basic rules which govern the filling of different atomic orbitals, the electronic configurations of different atoms can be written very easily. The electronic configuration of different atoms can be represented in two different ways. For example, notation form and orbital diagrams. In notation form, the subshell is represented by respective letters like S, P, D, F, as shown here in number 1, S, P, D, F. These represent the subshells, whereas the superscripts like letters A, B, and C, they represent the electrons in different shells. The similar subshell represented for different shells is differentiated by writing the principal number before the respective subshell. That means the principal number can be written before starting this represent notation. That is, the first letter will be the principal number, followed by the notations. In the second case, each orbital of subshell is represented by a box, as shown on the screen. This is a box which represents the orbital diagram. This represents a subshell, and the electron is represented by an arrow inside this box. This arrow can be pointing upwards for a positive spin, or the arrow can also point out downwards for a negative spin. The advantage of this orbital diagram is that it represents all the four quantum numbers. Take the case example of an hydrogen atom. Hydrogen has got only one electron which goes in the orbital with the lowest energy, namely 1s. So 1s with an arrow is written, is shown on the screen. The electronic configuration of the hydrogen atom is 1s to the power of 1, meaning that it has one electron in its 1s orbital. The second electron in helium, say for example, helium has got two electrons. The second electron in helium atom is represented by a downward electron. Therefore, for helium, 1s square is represented as shown. As said earlier, the two electrons differ from each other with the opposite spin, one pointing upward and the other pointing downwards, as can be seen from the orbital diagram. For other elements like lithium, barium, boron, carbon, nitrogen, oxygen, ferron, and neon, The configurations and the electron occupancy is shown in different subshells. For example, 1s for all the atoms are shown here, where there are 2 electrons. 2s also is shown. Similarly, we can write for other subshells in the notational form. Stability of completely filled and half-filled subshells. The completely filled and completely half-filled subshells are stable due to the following reasons. One is symmetrical distribution of electrons. It is well known that symmetry leads to stability. Completely filled or half-filled subshells have symmetrical distribution of electrons in them and are therefore more stable. Electrons in the same subshell have equal energy but different spatial distribution. Consequently, their shielding of one another is relatively small and the electrons are more strongly attracted by nucleus. The second stability factor is due to exchange of energy. The stabilizing effect arises when two or more electrons with the same spin are present in the degenerate orbitals of this subshell. These electrons tend to exchange their positions and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when subshell is either half filled or completely filled. I will read this para once again. The number of exchanges that can take place is maximum when subshell is either half filled or completely filled. As a result of this exchange, energy is maximum and so is the stability. Please see the diagram shown on the screen which shows the possible exchange for a d to the power of 5 configuration. This is 4 exchange by electron 1. This is electron 1, 4 exchanges taking place. Note that the exchange energy is at the basis of Hand's rule that the electrons which enter orbitals of equal energy have parallel spins as far as possible. In other words, the extra stability of the half-filled and completely filled subshell is due to one, relatively small shielding, or second one is smaller Coulombic repulsion. Coulombic repulsion energy, and the third one is larger energy exchange. This is 3 exchange by electron 2. And similarly 2 exchange by electron 3 and 1 exchange by electron 4 are shown on the screen. We have just concluded our lecture series on structure of atom. So we have covered all the 6 sections. Now we will quickly summarize the entire topic of structure of atom. We started with building blocks of elements. That is, we said that atoms are building blocks of elements. They were the smallest parts of element that can chemically react. First atomic theory, proposed by John Dalton in the year 1808, regarded atom as the ultimate indivisible particle of matter. Toward the end of the 19th century, it was proved experimentally that atoms are divisible and consist of three fundamental particles, namely electrons, protons, and neutrons. The discovery of these subatomic particles led to the proposal of various atomic models to explain the structure of atom. In the year 1898, Thomson proposed that an atom consists of uniform sphere of positive electricity with electrons embedded into it. This model, in which mass of electron is considered to be evenly spread over the atom, was proved wrong by Rutherford's famous alpha particle scattering experiment in 1909. Rutherford concluded that atom is made of tiny positively charged nucleus at its center with electrons revolving around it in circular orbits. The Rutherford model, which resembles the solar system, was no doubt an improvement over the Thomson model, but it could not account for the stability of the atom. That is, when the electron does not fall into the nucleus, why the electron does not fall to the nucleus. Further, it was also silent about the electronic structure of atoms, about the distribution of the relative energies of the electrons around the nucleus. The difficulties of Rutherford model were overcome by Niels Bohr in the year 1913 in his model of hydrogen atom. Bohr postulated that electron moves around the nucleus in circular orbits. Only certain orbits can exist, and each bit corresponds to a specific energy. Bohr calculated the energy of electrons in various orbits, and for each orbit he predicted the distance between the electrons and the nucleus. Bohr model, though offering a satisfactory model for explaining the spectra of hydrogen atom, could not explain the spectra of multi-electron atoms. The reason for this was soon discovered. In Bohr model, an electron is regarded as a charged particle, underline the charged particle, moving in a well-defined circular orbit about the nucleus. The wave character of the electron was ignored in Bohr's theory. An orbit is clearly defined path, and this path can completely be defined only if both exact position and exact velocity of electron at the same time are known. This is not possible according to Heisenberg. Heisenberg said that this is not possible to locate the exact position and exact velocity, and it was called Heisenberg's uncertainty principle. Bohr's model of hydrogen atom therefore not only ignores the dual behavior of electron but also contradicts Heisenberg's uncertainty principle. Erwin Schrodinger in the year 1926 proposed an equation called Schrodinger equation to describe the electron distribution in space and allowed energy levels in the atoms. This equation incorporates de Broglie's concept of wave-particle duality and is inconsistent with Heisenberg's uncertainty principle. When Schrodinger equation is solved for an electronic in an hydrogen atom, the solution gives the possible energy states and the electron can occupy and the corresponding wave functions psi, which in fact are the mathematical functions of electrons associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers: principal quantum number n, azimuthal quantum number L, and magnetic quantum number ML, arise as a natural consequence in solution of Schrodinger equation. The restrictions on the values of these three quantum numbers also come naturally from the solution. The quantum mechanical model of hydrogen atom successfully predicts all aspects of hydrogen atom spectrum, including some phenomena that could not be explained by Bohr model. According to quantum mechanical model of atom, the electron distribution of an atom consisting of a number of electrons is divided into shells. The shells in turn are thought to consist of one or more subshells, and subshells are assumed to be composed of one or more orbitals which the electron occupy. While the hydrogen and hydrogen-like systems like helium, lithium, etc., all orbitals within a given shell have the same energy. The energy of the orbital in a multi-electron atom depends upon the values of n and l. The lower the value of n plus l for an orbital, the lower is its energy. If two orbitals have the same n plus l value, the orbital with the value of n has lower energy. In an atom, many such orbitals are possible, and electrons are filled in those orbitals in order of increasing energy in accordance with Pauli exclusion principle. That is, no two electrons in an atom can have the same set of four quantum numbers, and Hund's rule of maximum multiplicity, pairing of electrons in the orbitals belonging to the same subshell, does not take place until each orbital belonging to that subshell has got one electron each. That is, it is singly occupied. This forms the basis of electronic structure of atom. I will continue the presentation by answering multiple choice questions. The first question: the probability of finding an electron at a point within an atom is proportional to. Please read the question again and I will give the choices. You have four choices. Option A, square of the orbital wave function psi square, orbital wave function psi, Hamiltonian operator, principal quantum number n. So you have to remember that the probability of finding an electron at a point within atom is proportional to psi square. So option A is given and you please mark it. Next question. Two electrons present in M shell will differ in. Four options are there. Principal quantum number, option A. Option B is azimuthal quantum number. Option C, magnetic quantum number. Option D, spin quantum number. So you examine, read it again and mark your answer. For electrons present in M shell, the value of the other quantum numbers are same, but the value of the spin quantum number will differ. Hence, two electrons present in M shell will differ in spin quantum number. It is given in option D. Please mark it. Next question. What is the lowest value of n that allows g orbital to exist? Option A 6, option B 7, option C 4 and option D 5. You please pause the video, think over and mark the correct answer and I will give the clarifications. For g orbital, value of L is 4. Since L is equal to n minus 1, n should be equal to 5. This option is available as option D. Next question. How many orbitals and electrons are associated with n is equal to 4? How many orbitals and electrons are associated with n is equal to 4? You have to remember and answer. Four options are given and you have to recall that when n is equal to 4, L is equal to 0, 1, comma 2, comma 3. Number of orbitals will be 1, 3, 5 and 7, that is equal to 16, and number of electrons will be 2, 6, 10 and 14, that's equal to 32. You can even use the formula number of orbitals is equal to n square, that is 4 square is 16, and number of electrons is equal to 2n square, that is 2 into 4 square, that is 32. This answer is available in as option B. Please mark it. Next question. An electron is in one of the third 3D orbitals. An electron is in one of the 3D orbitals. What are the possible values of N, L and ML for this electron? Four options are given. N is equal to 3, L is equal to 0 and ML is equal to 0. Option B, N is equal to 3, L is equal to 1, ML is equal to minus 1, 0 and plus 1. And C is N is equal to 3, L is equal to 2, ML is equal to minus 2, minus 1, 0, plus 1 and plus 2. And option D is N is equal to 3, L is equal to 3, ML is equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. Please examine and mark the correct answer. The correct answer is option C. You have to remember and mark it. Next question. The three d orbitals having electron density in all the three axes is, four options are given. Option A 3dxy, option B 3dz square, option C 3yz and option D 3dx 3d of zx. In dz square orbital, two lobes are lying along the z-axis and it contains the ring of negative charge surrounding the nucleus in xy plane. So, option B is the correct option. Mark it. Next question. Which of the following is responsible to rule out the existence of definite paths of trajectories or electrons? So, you have to read the question again. Which of the following is responsible to rule out the existence of definite paths or trajectories of electrons? So four options are given. One is Pauli's exclusion principle. Option B is Heisenberg's uncertainty principle. Option C is Hund's rule of maximum multiplicity. And option D is Aufbau principle. Please pause the video, think it over for some time and mark your answer, and I will give the correct answer. You have to remember that Heisenberg uncertainty principle rules out the existence of definite paths or trajectories of electrons, and option B is the correct answer. Please mark it. Next, which of the following properties of an atom could be explained by Thomson model of atom? Option A, overall neutrality of atom. B, option B, spectra of hydrogen atom. Option C, position of electrons, protons and neutrons in atom. And option D is stability of atom. You have to remember and mark the correct answer as overall neutrality of atom. So atom as such is neutral. We'll continue with some of the previous year's questions. According to law of photochemical equivalence, the energy absorbed in ergs per mole is given as, we have to mark the correct answer, and constant value value such as Planck's constant are given. Planck's constant, velocity of light and Avogadro number are also given in the question. This was in the NEET examination. So four options are given. You please read the four options, option A, option B, and option C and option D. So all the options involve numerical calculation. So you have to remember the correct formula, calculate the value and mark it. I will give the hint. So we know energy is equal to H into C into Na divided by lambda. Lambda is not given, so retain lambda as it is, and that E is given by HCNA. All the three values are given. Substitute and calculate and mark the correct answer as 1.196 into 10 to the power of 8 divided by lambda. So answer option A is the correct answer. Next question. 4d, 5p, 5f, 6p orbitals are arranged in the order of descending energy. The correct option is, this is also a neat question. So four options are given. So you please these four options and remember the answer. That is the logic. Higher value of n plus L for an orbital higher is its energy. However, if two different orbitals have the same n plus L, the orbital with lower value of n has the lowest energy. Therefore, the decreasing order of energy of the given orbital is 5f, 6p, 5p and 4d. So you mark it. Option B is correct because it has got 5f and the lowest is 4d. Next question. The electron in the hydrogen atom undergoes transition from higher orbitals to orbital of radius 211.6 pm. This transition is associated with. So it is a question in JEE mains examination. Four options are given: Paschen series, bracket series, Lyman series and Balmer series. So you have to remember and mark the correct answer as Balmer series. So you mark it, option D is the correct answer. Next question. Orbital having three angular nodes and three total nodes is option A 5p, option B 3d, option C 4f and option D 6d. You have to remember and mark the correct answer as 4f. With this we come to the end of unit 2 lecture 5. So we have completed the complete unit itself. In the next lecture, we will take up unit 3, that is classification of elements and periodicity in properties. Till then, goodbye.